In this video, we're going to go through a basic average velocity question. What we have, looking at our formula, is we see what is the definition of the average velocity. It is the change in position divided by the time interval. Now, we could be much more specific and say that the change in position is the final position minus the initial position, or any instantaneous position minus the initial position, and that the time interval is the time at any instant minus the initial time. So we have our definition, delta y over delta t, which is always true in every situation, and we can define it more specifically with y minus y naught, and the time interval we can define as t minus t naught, being more specific. And what we see across the top is the change in position is y minus y naught. And of course, that then is equal to y minus y naught is equal to delta y. So all of these terms in the numerator are equal to each other. Similarly, in the denominator, we have delta t. The time interval is t minus t naught. And that, of course, is equal to the delta t, the time interval, and t minus t naught. So what we have in these other expressions of the formula is different ways of expressing them. So we have y minus y naught, the very specific version of this, and we can combine the numerators and denominators in different combinations. So we can take this and combine it with the denominator to give us this equation. Or we could take the numerator, delta y, and combine it with the denominator over here to give us this version. So there's four different ways we could look at this formula, all coming from the basic definition of average velocity, which is always true, and the more specific expression of change in position and change in time. So now let us look at an example of Gigi. And we are told that Gigi goes to the store, and she covers 384 meters, and it takes her 249 seconds to do it. And she ends up at the store, and of course we're looking for the average velocity. So we could draw a picture of this to try and figure out what's going on, our reference frame, and we can have our 0 point in the positive direction and the negative direction. And so the question then is, where is the store? Where is the store? Well, we're not told. The store is just a location. It could be here in the negative, it could be at 0, it could be at the positive. We don't really know. And we know, what we do know is that she ended up at the store. So she ended up at the store, and it was 384 meters. And it took her 249 seconds. But the store could actually be over here in the negative, it could be at 0, it could be positive. We don't know which. But that means then is that this 384 is the change in position, and that the 249 seconds is the time interval. So we can do label our givens, delta y, 384 meters, and we can do our time interval, 249 seconds, and we are looking for the average velocity, which is unknown, and we would express that in meters per second. Now, since we're given delta y and delta t, we would use the first version of this equation. So average velocity is delta y over delta t. And we can put in 384 over 249. And we will end up with 1.5421686 meters per second. And again, we're recording our unrounded answer. So up until this point, we have our labeled picture, we've identified our givens, we've identified our unknown, we've identified the equation right here. We don't need to solve for the unknown because the unknown is already by itself. We substituted values, and we calculated and recorded the unrounded answer with units. So we're all the way down here. So the last step we need to do is evaluate this answer with the correct number of significant digits. Well, we started with this number on the top. It has 3, and the number on the bottom has 3, so that means our final answer can only have 3. So we underline these 3 to help guide us visually, and then we look at the next digit, which is a 2. A 2 does not cause us to round up, so that means we keep the digit 4. So our final answer is 1.54 meters per second. So we've dealt with the significant digits. Now the question is, do we need to express this in scientific notation? And as always, we are going to practice converting numbers and putting them in scientific notation because we may need to do that in the future. So we're just practicing. And what we look for is this number between 1 and 10? And again, the way we think of this visually is that if it is 10 or larger, or if it is less than 1, and we want to shade this 10 in because it includes a 10. If it is outside that range, it's in yellow, then we have to put it in scientific notation, and we can see that 1.54 is about right here. That 1.54 is right there, so it's already in the proper form of scientific notation. If the number had been 0.89, then it needs to go in scientific notation. If it had been 10.2, it would need to go in scientific notation. But since it is less than 10 and it is greater than 1, it's already in the correct scientific notation format, and that gives us our final answer, 1.54 meters per second.